How does the world around us work? An introduction to the scientific revolution. Before the days of the Renaissance and the Reformation, most of what people knew about the physical world, the universe and everything in it, came from the writings of the past, the texts of thinkers from ancient Greece and Rome, or from the Bible. There was no reason to question what Aristotle had said 1800 years before, because no one had the means to challenge what he had said, unless the Catholic Church disagreed with him. If the Church disagreed, then the Church was considered the ultimate authority on the matter. That began to change in the 1500s, as thinkers began to question the authority of the Catholic Church and investigate the statements of Aristotle. This became known as the scientific revolution, which was a new way to think about the natural or physical world. This new way of thinking required people to observe carefully the world around them and to ask questions of what had been accepted as fact. The ability to read and translate Muslim texts, to explore new areas of the world and interact with people who were before unknown, and then spread those new thoughts through printed works created by Gutenberg's movable type, allowed for these new thoughts to reach a wider audience than they would have experienced before. Perhaps the biggest area to be challenged was the idea of the universe. For thousands of years, it was believed that the Earth was the center of the universe and that the Sun, Moon, and other planets revolved in a perfectly circular orbit around it, with the stars in a fixed position on the outside. This was called the geocentric theory of the universe. After 25 years of study, a Polish astronomer, Nicholas Copernicus, released his heliocentric, or sun-centered view of the universe. Knowing that his view would not be accepted by most people, and that he did not want to face their negative comments, he did not publish his work until the last year of his life. Other scientists used Copernicus's work as a starting point for their own, coming to similar but somewhat different conclusions. It was not until Galileo Galilei built his own telescope in the early 1600s that Copernicus's theory would ultimately be proven correct. Using the telescope, Galileo was able to go beyond Copernicus's work, being able to see smaller objects in space and the surface of the moon and the sun. However, Galileo's work came under sharp attack from the Catholic Church, which ordered Galileo not to support the ideas of Copernicus. For just over 15 years, Galileo said and printed nothing, but instead wrote a book in which he presented both the geocentric and heliocentric view, but had a clear preference for the heliocentric. The Pope put Galileo on trial and was forced to sign a confession that Copernicus was wrong. Legend has it, however, that as he left his trial, he said, "And yet it moves." In 1992, Pope John Paul II officially acknowledged that Galileo was correct, over 350 years after his death. The work that Copernicus, Galileo, and other scientists were doing became the basis for what we know today as the scientific method. Scientists developed this logical procedure for collecting evidence and testing ideas. They would first come up with a problem or a question based on what they saw in the world around them, and then develop a hypothesis or a guess about that question. Once they formed that hypothesis, the scientists worked to gain evidence or conducted experiments to prove their hypothesis correct. Once they did that, the evidence or data was analyzed and interpreted to see if the hypothesis was correct and to help them reach new conclusions. Sir Isaac Newton used this approach to go beyond the work of Copernicus and Galileo to explain the force that kept all of the planets in their orbits and how things on Earth moved. That force was called gravity, and Newton believed that every object in the universe attracted every other object, with the amount of attraction being based on the mass or weight of each object. The more an object weighed, the greater amount of attraction it had. Based on that idea of gravitation, Newton developed three laws of motion. The first law of motion stated that an object at rest tends to stay at rest unless acted upon by an outside force. The same applies to an object in motion. This is also called the law of inertia. The second law of motion is that the momentum of an object is directly proportional to the force that is applied to it. The more force that is applied to an object, the faster it will move. The third law of motion is that for every action there is an equal and opposite reaction, so that whenever a force is applied to an object, that object applies an equal amount of force in return. As the scientific revolution spread around the world, advancements were made in the areas of medicine, chemistry, and the instruments the scientists used to examine the world around them. These scientists continued to ask questions about the physical world around them, which inspired other thinkers to question the role of people in each other's lives and what the government should be able to do about it.